Greetings, friends. We are here to talk a little bit more about quantum physics. So, before we get going, a couple of reminders. We'll have PLC 14 for Friday this week, and homework number 8, I think, is due Thursday. PLC 14, that's Friday. As of this recording, I'm still putting together the formatting of that, but it will be up a bit later today. We've got homework 8, which I believe is due Thursday. Is it Thursday or Wednesday? Oh, I can't remember. I think it's Thursday. Well, whichever one it's supposed to be. I forget. Whichever one it's supposed to be, we'll have a quiz that same day. Let's go ahead and continue on. So we were talking about the de Broglie wavelength of particles. We talked about how to kind of associate the wavelengths of the particles with their momenta. Basically, the idea of the light, right, in which light has a momentum and energy relationship. Light has an energy momentum relationship in which the energy is hc over lambda, and therefore the momentum of the light is h over lambda. And that's due to a number of different things, but the point is that this is kind of where we are right now. And what de Broglie said was that this could also be applied to material particles such that they then had a wavelength that was given by their momentum. So this is h over p, and we had just finished calculating a couple of wavelengths of particles, and then we had talked a little bit about the uncertainty principle, in which we can't for sure give good precision. We can't give as much precision as we'd like to the measurements of positions and momenta. Okay, so this was the idea that the delta x times the delta p is greater than or equal to h bar over 2. And just to remind you that h bar is h divided by 2 pi. All right, so we had talked about the uncertainty principle, and I looked at the uncertainty of maybe it was a dust particle or something like that, and the uncertainty of an electron. So I just want to revisit those real quick and talk quickly about what this means, because I made a step in there that I was a little bit rushed on, so I just want to expand a little bit on that. So let's go back to the one where we did the electron in confined within an atom. And so it's confined within a distance of about 1 nanometer, right? So half a nanometer on each side. So this is confined to a 1 nanometer kind of box or space, whatever you like to think of it. In other words, we know its position is somewhere in, within, say, like between here and here. This is 1 nanometer. This is not 1 nanometer really, but that's okay. Suppose that there's an electron and we know it's within here somewhere. Therefore, the biggest uncertainty that we have is, well, the electron could be really close to this pen, but I'm not sure, and this one's a nanometer away. So the uncertainty that we have in its position is essentially 1 nanometer. What that means is, if I consider that to be a standard deviation, what I would say is then the standard deviation here is our best guess of where the particle is, and then the standard deviation would say about here to here. Those are both one standard deviation wide, and so I would call this the mean, call it maybe x bar, this is position, and this is x bar minus a delta x, and this over here is x bar plus a delta x. And so delta x is acting as the standard deviation. So we're fairly certain it lies somewhere within here. Well, really that's plus or minus a half the delta x. I should be careful with that because I called that this. So the entire thing is that. So this is really half of that. This is really half delta x. And this is really, oh, I'm just gonna put it over 2. All right, there you go. Such that the entire uncertainty was delta x. Okay, sorry about that. That makes better sense. So we're fairly certain that it lies within this region. All right, and that's what standard deviation means. I went in to talk about what the uncertainty and the momentum is then going to be. Delta P is then, at the very least, what's the minimum uncertainty in the momentum? Okay, so I said it was going to be h bar divided by 2 and divided by the delta x of 1 nanometer. And then you say, what's the uncertainty in the speed? Okay, and so what you do is you say that the uncertainty in the momentum is m times the delta v, and then you can end up dividing the m underneath. Okay, so that gives us a way to talk about what the uncertainty in the speed of the electron is going to be if it's confined. So we have h bar divided by 2m and delta x. And I think with the numbers that we had, it worked out to be something like 10 to the 6th or 10 to the 7th or something along those lines. Should probably go back in and redo that, but it's some large number, right? So let's say it's around 10 to the 7 meters per second. I don't quite remember exactly what it was, but let's just pretend that that's what it was. Okay, so what does this tell us? Now, if we are trying to assume that the electron is at rest, so supposing that we go back to the question I asked earlier, which was, why does the electron not just sit right on top of the nucleus, right? And if that were the case, then the electron would be sitting here on top of the nucleus and it would be not moving. And we would have a fairly good idea of where it was. In other words, our precision in the position would be much less than this here. It would be more like a femtometer instead of a nanometer. And our uncertainty in the momentum would basically be 0 because the momentum itself is 0. Okay? So now, if we're considering the electron sitting on top of the proton, or on top of the nucleus if you like, then we're saying we're considering its average speed to be 0. And therefore, if I think of this type of uncertainty in the speed, and forgive me if that's the wrong number, but let's just pretend, then I want to go back to giving that number physical meaning by looking at something like this. And what this would tell me is then that I think that the average velocity of the particle might be 0. So imagine I'm drawing this again, but now with velocity in mind. Okay? So now I have something that looks more like this. And I'm going to say, all right, here, its average velocity should be 0. This is the v equals 0 line right here, because it's sitting right on top of the nucleus. And I would assume that that means it's not moving. But we are uncertain in its velocity to this much. And therefore, that would again play the role of a standard deviation, which means that if I look here, and this is v bar minus 1/2 delta v, and this is v bar plus 1/2 delta v, that the entire situation here of its uncertain velocity means that it could then have a velocity that is somewhere about that size. Okay? So it's not only that we're uncertain in the velocity to this much, but we're also saying that that can also approximate what the actual speed of the electron is because at its biggest, right? Because we're assuming that it was at rest. Its average velocity is zero. Okay, so when you think about particles, and you're saying, well, I think it's average. I think it should have a velocity of zero in this direction. That makes the uncertainty in that direction very large, usually. You're right for a small confinement. Okay. So let's go and think about then. If I have particles in a tube or something, maybe I have a tube. Just as another example of this, suppose I have a dust particle in a tube. And I'm thinking that it's confined within the tube, and I'm also thinking it's at rest. It's at rest within the tube. So here, okay, I've got a tube. And let's say the tube is 10 microns wide, like so. And I've got a dust particle in here, and it's just sitting right here, and I'm going to assume that its average velocity is zero. Okay, so then I'm going to ask, okay, what is my uncertainty in that velocity? And I'd go through the same exact analysis. So I'd find that my dust particle, my uncertainty in where it is, well, it's somewhere in there. So my uncertainty in where it is would be the length of the tube, okay? And then I would go through and divide mass off. I would have to know something about the mass of the dust particle and figure out what the uncertainty in the velocity is. But I'm assuming that the average velocity of the dust particle is zero. Therefore, I would be able to say whatever this result was for my dust particle here, I would be able to say that that is indicative of what its velocity is. Okay, so it's that key to saying that we are considering the average velocity to be zero, and therefore it could have a velocity of this much, is why we're able to say that. Okay, so there's a little bit on that. I want to talk a little bit more now about the process by which we extend the wave picture to the particles. Okay. Now, a little bit of back pain there. That was fun. Now, if you want to find out a little bit more about this, I will say that Feynman has a great video on this. If you search for Feynman in I believe it was the Messenger lectures, the meaning of quantum theory or something like that, he's got a full 1 hour talk on kind of the underpinnings and the mentalities behind quantum mechanics. I'll go through, I enjoyed what he says, so I kind of pattern what I'm going to say off what he's saying. But if you want a more thorough discussion of this, I'm going to refer you to his video, which is really, really good. So Feynman, it's a Messenger lecture. Whoops, Messenger. And I think it's number 6. And it's on the kind of the mentalities of quantum theory. So that's on YouTube, so go take a look at that. If you have a spare hour and you are interested, it will be fascinating from several points, not one particular one, but several of them. And one of which would be just listening to the guy talk. I've heard him compared to a taxi driver in New York City in the 1970s, which is not far from the truth, being as how he's born in Long Island. So I will kind of take a little bit of that and we'll go forwards with it. So we are used to our double slit experiment. So I'm going to return to that, and I'm going to return to it with light. So we know what we're going to get, right? In the sense that we've done a lot of analysis on this exact procedure. What I'd like to do is use that experience to introduce another way of looking at it. And then we'll go a little bit further with that. The double slit experiment with waves of light. So what happens here, okay, so light is coming in, we'll assume that it has a relatively constant wavelength. Right, and it's going this way. So here's our wavelengths. Like that. So those are the crests, perhaps. And so the wavelength would be the distance between those crests, and it's traveling to the right, and it's about to impinge on the double slit. Once it does that, then we were pretty confident in saying, okay, each one of these acts like its own source of waves, right, the top and the bottom, and therefore when I look at the screen over here, then I get a pattern of bright and dark fringes. Now, what I'm going to do is, again, I'm going to assume that these slits are narrow enough such that the central diffraction maximum is large. All right, so I'm just really looking at within the central diffraction maximum here. Let's see, our straight across point would be slightly under that line, so it'd be right about there. We'd expect a central interference maximum right at that point, so let's suppose that it's out here. Like that, and then we're going to have another one right up here, like that, and another one right up here. Whoops, should be a little bit farther up than that, like so. And so these are our interference peaks. This is a bright spot, and it's located right here. This is our central bright spot. And of course we have the dark spot here. So if I were to, and then the same is true down here. So if I were to say, okay, thinking of the intensities, we have large intensities of light at different points here, here, and here, and zero intensity in between. Okay, we don't expect any light to hit here. Now let's introduce a little bit of a further step in which, because we have analyzed the photoelectric effect, and because we looked at the Compton scattering effect experiment, we now know that light carries a photon-like quality to it, which means that if we then consider this incoming light, rather than it being a large number of waves, to be a stream of photons. Okay? So now if we consider this instead to be a stream of photons coming into the double slit experiment, what is it that we're going to perceive here on the screen? Well, the exact same thing. Light does not care what we think of it. A great way to go through life, by the way. But light literally does not care. So it's going to do the exact same thing, whether we think it's wave-like or we think it's a stream of particles. All right, we will get the same interference pattern. So this is your interference pattern, as it's called. Okay, is on the screen there. And so if we consider the analysis of it from a particle-like point of view, then we notice a couple of things. Excuse me. We notice a couple of things. One of them is that if I make this light very, very, very dim. And we would have to probably mostly imagine how to do this, but nonetheless, if I were shooting through just, instead of hordes of photons coming through this, if I dialed it way down, so it's just a couple at a time, and I look at what the pattern is on the screen, I will see particular bright dots. And the bright dots are where the photon has landed on the screen, okay? What we do not see is if a photon comes through the slits, we don't suddenly see 2 points on the screen due to the photon having split in half. We don't see that. We see one photon in, one photon hitting the screen, okay? One in, one hits, one in, one hits. Not one in, and then two that are slightly dimmer hit here and here. That's not what we ever see, okay? So that's one thing to think about. The photons do not split up. Second thing, we consider the intensity of the interference pattern to be related to the number of photons that are landing at that point. In other words, here at the central maximum, I consider there to be a large number of photons landing there. I consider there to be a large number of photons landing at these bright spots here and here, okay? I consider there to be basically no photons landing here. So if I were to draw a population like a bunch of dots, simulating what you would see on a screen, right? This is not what you see on the screen. This is just the intensity pattern. What you would see on the screen, let's see if I can do that maybe right here. Here's the screen, okay? I'm gonna draw it again, okay? Same thing, but now I'm gonna put a bunch of dots in here to show you what the screen might look like if we looked at it kind of from this perspective. I'd see a large number of dots here at the central maximum, and that's between here and here, so we'll go from there. Wait, where was it? Right there to right there. All right. Okay, so I'm going to see a large number of dots, okay, all right around in here. That's the central maximum. Okay, I'm going to see fewer and fewer dots out here. All of a sudden, I'm going to have a little piece right here where there are none. And then I'm going to start the whole thing all over again. Where's my next minimum? It's way down here. Okay, so what I'm hoping that you can kind of see from this, there's a great density of dots right in this region here and in this region here. You may not be able to actually get the clarity on that. Maybe I can just move you a little closer. All right, let's see if I can just pick you up here and move you in so that you're looking at my dots. Okay, so a large density of dots here, large density of dots right here, and then kind of spreading out a little bit, less dense right around that. But then notice that well, I only really did one spot. There's one spot right here with no dots whatsoever. It's like there's a little bald spot right here, right? And then the whole pattern starts again. The reason for that is because right across from this is the central max, big intensity right there, okay? Same thing here, big intensity right there. So we should be seeing large numbers of photons landing at those points. All right. Whoa, hopefully that helped, even though it maybe made you seasick. And if so, I apologize for that. So the intensity of the light we are now going to start considering is related to the probability that a photon lands there. Because it's much more probable that photons land here. And what do I mean by probability? I mean the number that has landed within here compared to the total number. Okay? So probability of landing at a certain spot at a certain, I don't want to say one particular point, so I want to say it's in a certain area. So let's have it land in a certain area. Okay. And so what area is that? Let me show you. I just got to erase this first. So, for example, the area could be, I could just take a small area right here and say this area right here. I'll make it a little bigger than that. Okay. So suppose that I extended it way beyond the screen just so you could see it a little bit better, because I think that it's probably going to be hard for you to see the pattern based on what I've heard about the video quality, and so sorry about that. But let's suppose that this is at a certain distance. So here is the central maximum point here, and so it's some distance x, or y, sorry, we called it y, down from there, and I'll say that the area here has a width of, for example, delta y. Therefore, the probability of landing in a certain area at a certain area of width delta y, okay, is related to the number that landed in there divided by the total number. So that is how many photons actually landed in this thing. In this case, there's 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, 8. There's 8 dots in my strip right here. And I don't know how many I made, but it looks like a couple hundred, maybe 200, 150, 200 dots maybe here. So the probability is 8 in 150, for example. Okay. So this, for example, could work out to be 8 divided by 150, and that is the probability of landing in that particular strip. Now, if I move the strip, I change the probability, right? Because if I move the strip, and all of a sudden I'm right here on top of the central maximum, well, that's going to encompass a large number of dots. And the probability, or the fraction of dots, is going to be much larger compared to the total number, right? So the probability will be higher for the photons to land here. Okay, so this is now the double slit experiment with photons. The point being here that we are relating the probability of landing in a certain area to essentially the wave amplitude squared. The reason that we're doing that is because the wave amplitude squared is related to the intensity. So what we're really doing is saying the probability is related to the intensity. And that hopefully makes sense, because it's kind of experimental, right? You land there, there's a bunch of them there. Less of them land over here, none of them land right there, and then a whole bunch land down here. So the probability is basically related to the intensity. I will say then the probability is proportional to intensity. And that is the square of the wave amplitude. Okay, so we would say it's proportional to, for example, amplitude squared. For example, something like that, if you like the mathematical viewpoint. Alrighty, now let's take a look at an experiment. Oh man, I cannot do that. Let's take a look at an experiment where we do the exact same thing, but since we're looking at photons and the particle-like view of light, let's take a look at the same exact experiment from the electron point of view. What if, instead of photons, we shot electrons at this thing? So, we're going to get a double slit with electrons. So here we go, we got a double slit experiment. And over here, I've got something that is shooting electrons. Some type of, right, boom. Electrons coming out of here. This is an electron gun. I'm not supposed to say the word gun anymore. It's an electron emitter. Okay, what do we find when we do this? Well, from an analysis of the electrons, we know that, well, I'm giving them momentum coming out of the emitter here, okay? So they're coming out of the emitter. We know that they have momentum, okay? Now, our classical thinking viewpoint will be that these electrons are bits of matter, right? This is what we have been taught. Electrons are bits of matter. And therefore, they are going to make a shadow of the double slit on the screen. If I consider the electrons to be just essentially bits flying through the two slits, right? Some of them will hit up here and they won't go through. Some will hit right in the middle, they won't go through. Some of them will pass straight through the slit and come straight through and make a peak right here. Let me actually just draw another screen here. Okay, this is the bits of matter screen. This is what we would expect to see if electrons were just chunks of material. Okay, we'd see them coming through here. They'd be emitted. They'd be coming through here. We get a lot of them right in here, right? We get a lot of them right there. We would not get any directly straight across because the double slit is blocking them. We would, however, get another peak right around here, say, where they're landing. A large number of them are landing there. And of course, there's going to be other bits. You'll sometimes find some that are spurious, way out here, way out there. But that's because they hit the side of the thing and ricocheted off or did something strange, right? But for the most part, if we consider electrons to be bits of matter, this is the pattern we will expect. Okay? This is the pattern that we will expect. I'm going to make this a little bit better here. So this is reaching 0 there. I'm just going to adjust the peak height so that they match. And we don't consider this anything to be wrong here. There's something like that. All right, so there's something like that. So high probability of a bit of matter landing there, high probability of a bit of matter landing there, and that's because they're directly across from the slits. And so, in fact, if you do this and you fire, say, golf balls or BBs or something like that at a screen, this is what you're going to see. You're going to have a detector, by which I mean you'll have, say, a box of sand or something, and you'll say, oh, I'm going to collect a lot of them right here. I'm not going to collect any right here because they didn't make it straight through the slit. I'm going to collect a large number of them here. Okay? Now, of course, you may or may not be aware of this, but when we actually do this experiment with electrons, of course, this is not what we see. We see this pattern. This pattern is the interference pattern. And because electrons, as I was beginning to say, have a wavelength that's associated with their momentum, we can say that they are kind of waving through the two slits and interfering on the screen here. Okay? Now, I will say this. Like light and photons, if we make the source very, very slow, very dim, not much happening on the emission side here, one every little bit of time. No problem to do that with electrons. I fire one electron out, and same idea, I find one electron hitting the screen. Okay? Electrons do not shift into suddenly two pieces, or they don't split up. I don't find a little bit. I don't find that. One emitted, one hits the screen. Right? So they leave particular dots. They are intact, in other words. Okay. So with that being said, when I run this experiment, what do I find? I find exactly the same thing. as I did here with the dots of the photons. Because they are landing on the screen, and I'm finding individual dots, right? So that's very much the same. And I'm also finding that they prefer to land in particular places, and there are some places where they do not land. In other words, the electrons coming through this double-slit experiment exhibit the exact same behavior as the light. There is an interference pattern. So this is what we think we would observe, but in fact, this is what we do observe. Okay, like this. So this is the actual result of experimentally when you fire electrons through a double-slit experiment, like this one. Okay? The same exact thing happens. I think I mislined up the central maximum here. Sorry about that. So these kind of shifted. But you can imagine my central bright spot is still directly across from the place where I was saying there should be none landing. All right? Because electrons exhibit this wave characteristic, we are then going to move to the same line of reasoning as we just had with the light and the photons. I'm going to say there's a probability of landing in a certain area. And that's going to be related to the number I find in there divided by the number that I shot at the screen in total. And therefore, that the probability of landing on the screen is actually not what we would call the intensity for the electrons, but we have to now invent another quantity to try and describe what for light was a wave amplitude. Electrons have a de Broglie wavelength, but as to what their amplitude is, we don't know. So we have to invent a new quantity to try and describe this probability such that when we square it, we can get something about the probability. All right? Now, before I go into that, because I have limited board space, what I'd like to do right now is go back to this for a minute and show you, sorry, I'm going to move this a little bit. All right, I want to talk to you real quick about what's going on here. This is what is expected, so I'll put expected. Okay, and this is actually not what happens if I have two slits open. But there are some caveats to that. Okay, so let's talk. Even if I shoot one electron through the double slit at a time, I still find the interference pattern on the screen. What does that mean for us? What that means for us is that somehow you have to discount this picture. Because if I fire one electron through at a time, and I still get an interference pattern, which we do, then effectively all of my thinking that went into here has to be questioned. The main thing that went into thinking about this was the following assumption. When I fired an electron, it went either through the top slit or through the bottom slit. That was my main assumption in creating this pattern right here. The electron got fired, and either it went up through here and made a pattern there, or it went through this one down here and made the pattern over here. Therefore, this assumption must be incorrect, because this is not the pattern we see. That pattern is based on the assumption that the electron goes through either that slit or that slit. But we do not see that pattern, we see this pattern. This pattern is therefore telling us that I consider that assumption to be wrong. Therefore, when one electron comes through here, it must come through both slits at the same time and interfere with itself. How does it do that? Well, we don't know, but what we can say is the wavelength with which it leaves from these two slits is fairly well defined. It's the de Broglie wavelength, which I erased. I don't remember where I wrote it, but it's h over p. We know the momentum of the outgoing electrons. Whatever it is about the electron that is causing it to have wave-like behavior must be coming through these two slits and interfering with itself such that it creates an interference pattern on the screen because it has a large probability of landing in this spot or this spot and very little probability of landing in here. So whatever the whatever the electron is doing, its wave behavior is described by this result. Okay? And each electron must be going through both slits at the same time, because there isn't another electron for it to interfere with. If I shoot one electron at a time, remember, it doesn't divide up. We never find that. It's like divides up and comes back together. This is crazy talk. Okay, that can't happen. So, well, let me put it this way. That doesn't happen. There's no reason for something like that to happen. Let me put it that way. There's no internal mechanism for the electron. It's one thing. It comes through both slits at the same time, and it doesn't interfere with another one on its way. Okay, so fine. Let's do the following experiment. I'm going to cover up the bottom slit. When I do that, what do I find? I find exactly this pattern. I cover up this slit, this peak right here, and I find the electrons going through here. Okay. If I cover up this slit, I find the electrons coming through here. So by covering up half of the experimental apparatus here, I go back to having this pattern. Why do I go back to doing that? Because I have confined the electrons. I have forced them to do something I want them to do, which is I will now have you travel through the top slit, and they go, okay, we're traveling through the top slit, and they go through, and they come in, and they get here. Okay? And the same thing happens down with the bottom slit. If I force them to go through the bottom slit, they'll do it. Now, if I open up both slits, I get back to this pattern, which is clearly not the addition of these two split by themselves. It's clearly not an addition of what happens with the single slit, the top slit and the bottom slit at the same time, right? This is clearly not the addition of one plus the other. And part of that comes from what interference means. If you look at it from a mathematical perspective, essentially what you're saying here is that there's some intensity that comes through here, call it A, and there's some intensity that comes through here, call it B, such that if I covered up B, I get A squared as an intensity. If I covered up B, if I covered up A, I get B squared as the intensity. I said A and B are intensities. Sorry, that's not true. Amplitudes, wave amplitudes. Wave amplitude A and wave amplitude B, such that I get A squared as the intensity here, B squared as the intensity here. But when I let them both go together, I must be getting A plus B, that whole thing squared. And if you know how to multiply out a quadratic, it's not just A squared plus B squared. It's got that cross term in it. That cross term is the interference term that causes the interference pattern here. All right? So, furthermore, if I do an experiment to try and figure out, while this is running and I have both slits open, and I want to figure out, did the electron go through slit A? And whenever it goes through slit A, I'm going to be really clever about this, and I'm going to put a little light right back here that's going to shine light upwards, and anything that comes through slit A, I ding the light on. It's already chosen to go through slit A. I pop the light on, see if it's there. If it's there, I'll see it. Okay? So that means it's already made a choice about where it's going to go, and if it's up here, I'll get a reflection. And as soon as I do that, you know what happens? I get a bunch of particles landing at A, or a bunch of particles landing here across from this slit. I get a bunch of particles landing over here. And I don't get the interference term any longer. There's no interference. Because what am I doing? I'm forcing the electron then, I knew you went through the top slit, so it goes, yep, I went through the top slit, and so I land there. Which means that the ones that didn't go through the top slit, must have gone through the bottom slit, and they land there. And they go, okay, we did went through the bottom slit. So when you try to observe, the pattern changes. And this is a fundamental tenet of quantum mechanics. Our observations
how do we make them? If I want to know where an electron is, how do I find that out? Well, I shine light on it. But the light, remember the billiard ball experiment, right? If you have the dark room with the billiard ball table and you have a ball and you're trying to find where another one is, and you do, and you roll it, and it click, and they go off. It used to be right there, but it's not there anymore. I have no idea where it is now, right? And this means that if I shine light on an electron that's coming through here, and I go, aha, you're there now, and you're on your way to here, it kicks it, right? It destroys whatever it was doing. So it's the electron's interaction with the photon that I'm shining on it causes the electron's behavior to change. And this is something that is both describable and not describable at the same time. Very, very interesting. Anyways, because we have an entire theory about how matter interacts with light, and it's really successful. It's probably one of the most successful theories that we have in terms of predicting what's going to happen. It lands on precision almost every single time. Yet we don't quite know exactly how it works, but we know how to describe it. Okay, so that notwithstanding, the electron does have wave characteristics. It does go through both slits. It does produce an interference pattern. So matter goes through slits and produces an interference pattern. And I referred to this a little bit before when I talked about the diffraction of large matter going through a single slit. Single slit will diffract things like electrons and molecules and things like that. Okay, so let's go back now and start talking a little bit more about what this probability thing is going to do for us. Okay. So from the perspective of mathematics, essentially we are free to choose whatever we want to do here. Now, with light, we have this whole thing with what's the wave intensity and the wave amplitude. We're going to square the wave amplitude to get the intensity and blah, 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 blah. And there's so on and so forth with that. Okay? I'm not going to spend a bunch of time talking about that. But with the electrons, we don't have this already in place. Because we had a whole theory about light being a wave, we had a whole bunch of stuff in place how to mathematically describe these waves. We do not have a whole theory, we do now, but for us right now, chronologically speaking, we don't have any way of describing the electrons other than the wavelength and the de Broglie wavelength. So we are now free to choose how do we calculate this probability. So what we're going to do is we're going to calculate the probability by assuming that there's a wave, there's a function which describes the wave characteristics of the electron. And so we're going to try and assume that we have the ability to calculate what that function is and have it tell us something about the electron and its position and its momentum and things like that. This function that describes the waves of the electrons is known as the wave function. And it has Greek letter pitchfork, which is called psi, as its character. Okay, so the wave function is describing something about the probability of the electron. Now, it's not describing the probability because, and we'll go into this a little bit in a few minutes, but the idea is, remember, this is the probability of landing in a certain area, and that probability is proportional to the intensity. So really, this intensity is really a probability of landing in a certain area. That means it's more like a density. Okay? It's the probability of landing between here and here, or between here and here, or between here and here. There's a probability for each one of those. And that is because it depends on how much distance you have between the two endpoints of your area, or the space that you want to look at. There's a probability of it landing in here. We call that the probability density, because it depends on what your length is. So we adopt the same point of view with the wave function. We say that the probability of landing at a certain delta y is the same basic definition. It's the number that we find there divided by the total number. But since we are free to choose what we do with this wave function, and we don't already have a whole bunch of ideas of what the intensities are and things like that wave-wise, what we just say is this is equal to, in the same way that we squared the amplitude of the light, we say that this is equal to the square of the wave function. Okay? So that's the probability density. And then if we want to find the actual probability of it landing in a certain delta y, well, it depends on how big the delta y is. If I made a delta y that was much larger, then I'd have a much greater probability, right? So I have to multiply this by delta y in order to figure out what the actual probability is. Therefore, what we do is we call this thing a probability density. Because it's the probability per length. In other words, we have to multiply by a length in order to get a probability. Okay? All right. Now, there are a few things that are really useful to know about this, and that is that if I shoot an electron through the double slit experiment, it will land somewhere. It's not going to disappear. It's there. And it can't just disappear. It could just disappear, but nonetheless, it won't. And if I'm just shooting the things through here, it should be somewhere. In other words, if I add the probability of delta y, well, hold on, let me backtrack. If I say, okay, I'm shooting the one electron through here, and I just did one electron, and it went through the two slits, and I'm looking with my detector, what's the probability of finding it here, anywhere? What's this probability? I know I will find it somewhere. And therefore, I should have a 100% chance of, as far up and as far down as I go, it will be detectable somewhere. Therefore, what we do is we say probability of the electron landing somewhere has to equal 1. Is equal to 1, which is, in other words, it's 100% that it resides somewhere. We don't know where, though. And what this condition is known as is it's called normalization. In other words, we can't just have a bunch of probabilities adding up to whatever we want. They have to add up to 1. So if I look at a single electron and I say, well, I'm going to shoot this at a two-slit experiment, and I have a probability that it'll land here of 25%, and a probability that it'll land here of 25%. I got a probability to land here of 0%, probability to land up here of 10%, and it'll land down here at 5%, and 6%. Right? I'm going to add all those up. That should equal 1. Okay? It should, or 100%. I should be able to find the thing somewhere. So that's called making it normal. And how do you mathematically make it normal? You do that by forcing all the probabilities, all the probability densities to add to 1 when I add them all up. Okay? So I say that this mathematical process is to add each individual probability density over each individual strip, and I add them all up. Add all psi squared delta y's. How do we do that? Well, mathematically, it's an integral. And we say that it's integrate. Now, from somewhere to somewhere else, I know I can put as big of limits as here as I want because it's got to be somewhere. And if I can't find it within minus infinity to plus infinity, then it's disappeared and something has gone vastly wrong. I'm going to use dy here instead of delta y or x, and that should equal 1. And so we say that this is the way you normalize a wave function, okay, by making it such that its probabilities add up to 1. Okay. Now, let's take a look at what this means in a little bit more concrete perspective. And then we'll step back a little bit and talk about what this means from a slightly more philosophical perspective or a mental viewpoint here. Let's take an example in which I have a wave function and I want to just come up with a trial wave function. So let me come up with a trial wave function that looks like what? Let's suppose that I have one. Let's suppose that we have maybe that'll work. AE to the minus x, where the x is in absolute value bars, so that it doesn't matter if I'm on the positive side of the x-axis or the negative side of the x-axis, it still does the same dying exponential behavior. What does this look like? By the way, this is going to be a big part of what we're going to start undertaking, learning to draw wave functions. So let's start getting used to doing this. Every time you see a wave function, think about, okay, what does this look like? And start drawing it out. So let's go ahead and do that. This is psi as a function of x. I should probably move this over, shouldn't I? Because I'm running into that. So let's go over here. Do it over here. Psi of x. Like this. Okay, now, what does it look like? Well, it's a dying exponential. So if x is equal to 0, you can see that the quantity is equal to a. The wave function is equal to a at the on the vertical axis. And once it starts going away from that, it's going to be dying off, which means it should be looking like this. And if I go to the negative side of the axis, it should do the exact same thing because it's absolute value. So it should look like this. A mirror image of what I had on the other side. So if I were to try and integrate that, well, actually, let me step back before we do that. Suppose that I want to say, how would I find the probability of the electron being at a certain point on the axis? Sorry, I didn't label the axis here. There. How would I find the probability of locating the electron at a certain point? Well, I use this as my guide. In other words, I'm going to pick an area or right, which has a width to it. And I'm going to say, okay, suppose that I'm interested in finding what the probability of the electron is when it's in here. Like this. This strip is, say, dx wide. And I know I use dy over here, but it's just d whatever this axis is. And usually it's x because that's the horizontal axis. All right, so what I would do, if I wanted to find the probability of the electron being in there, I would need to know how far away I am, right? Because I need to give the wave function some value, and then I need to find what's the strip of this area here. How big is that strip? Well, how much area is under that strip? Okay, so I need a strip of length of width dx. And I need the value of the function here and there, and that would give me my area. Now, hopefully you can kind of imagine that if this really was a wave function, that the probability of it landing somewhere, right, should be 1. It should be somewhere here. We just don't know where. So the probability is found by doing that. What you would do then to find the normalization, what does normalization do? It finds you your constant A. This here is found by normalizing. In other words, I take this wave function and I say, okay, 1 is equal to the integral of minus infinity to plus infinity of psi squared, which is a squared, times e to the minus 2x, and I'm going to integrate that dx, like so. All right, now since this is a mirror image of one another, right? I could easily divide this integral into 2 parts. I could say that's equal to 2 of 0 to infinities of a squared, and that would give me the ability to take the absolute value off this thing, e to the minus 2x dx, like so. I'm going to erase some of this. Okay. All right, so to find the constant a, what I do is I just have to solve through for this thing. So integrating e to the minus 2x from 0 to infinity, I have 1 equaling 2 integral 0 to plus infinity e to the, a squared. I'm going to pull the a squared out of the integral. It's a constant, e to the minus 2x dx. So this integral here, let's see, what do you do when you integrate e? If you differentiate it, it just comes down, you get the same thing. So this has to go underneath, right? So I should get something like e to the minus 2x divided by minus 2. Is that right? So if I differentiate this thing, I would get e to the minus, I would bring out a minus 2 and it would cancel that thing and I would get that back. That sounds right. So let's do this. I would get e to the minus 2 here, and that's going to cancel with the 2 out in front. And I'm going to evaluate this thing. So this is going to be evaluated 0 to infinity. All right, so if I evaluate it at infinity, this becomes 0. And then I'm going to subtract off the value at 0, which is 1. And that's going to be 1 with a minus on it. So this is going to be 1/2 minus 1/2. Right? So those two go away. And that means then that this thing, I would be multiplying 2a squared multiplied by the plus 1/2 from the results of the integration here. And so these would go away. And then I would get that a is equal to 1. Let's see, hopefully I got that okay. Let me just make sure if I'm thinking of this right. 2 squared, I did this right? I squared squared that. I think I got that. So if I differentiated that, I get minus 2 e to the minus 2x. So that looks okay. Alrighty? So that's how you figure out a from normalization. Okay. So that's a little bit about what the wave function means. We're going to return to more physical properties of the wave function in a little while. Probably not today, but kind of going on through the rest of this week. Before we leave today, I want to introduce you to, just like Newton's laws, right? You have a concept of something. You have, for example, I want to talk about the force. I want to talk about things that have experiencing forces and net forces, and what kind of relationship the forces produce with its motion, like its acceleration. Okay, so I'd say, well, Newton's second law tells me about what the net force is, and it tells me what its rate of change of momentum is, or it tells me what its constant mass acceleration is going to be, or it tells me something. Okay, so there's a productive point of view by which you can do this. So there is another one that also involves the wave function. And it happens to be known as the Schrödinger equation. Now, the Schrödinger equation is essentially a conservation of energy equation, but it's kind of tweaked so that it works for waves and wave-like objects. It comes out of energy conservation. So let me kind of tell you what this means. What this means is I take the kinetic energy of the particle plus its potential energy. So whatever potential energy it's feeling, a lot of the times this is electromagnetic in nature because we're talking about the behavior of electrons. Electrons carry a negative electrical charge, and therefore they are subject to feeling forces and feeling potentials from other electric charges. So a lot of the times the potential energy is an electric or electromagnetic thing, and this is equal to the total energy. This is not a very surprising relationship here. It probably is one that you've known about for a long time. But cast in the form of something that will help us figure out behaviors of quantum particles, this is going to look a lot different. Okay? So the kinetic energy looks a little bit different than what you're used to. All right? In fact, instead of being 1/2 mv squared, and by the way, we are going to be non-relativistic for this. We are not going to go into relativistic kinetic energies. That's a whole other step. But thinking about the non-relativistic form of the kinetic energy of 1/2 mv squared, well, we can't quite use that because what do we mean by m and v and all this kind of stuff? So thinking of how this works, you end up with an equation which you can motivate this. I'm going to just tell you that it's out of conservation of energy. I'll tell you what the individual terms are. Like this. All right, that's the kinetic energy operator. It's negative h bar squared divided by 2 mass, 2m, and it's the second derivative of the wave function with respect to distance. Plus a potential, which I'll just call v, multiplying the wave function again, and that's going to equal the total energy, which I'll just call total E, multiplying the wave function again. Okay? Now, this is the time-independent version. Okay? If you're more interested in the time-dependent version, it looks a little bit more like this. You'll notice that there's a negative IH bar d by dt on the left side here. On my left side. So that this part here, we've dealt with some things that go along with that, and we're just saying, well, it's basically just a conservation of energy. So it's kinetic energy plus potential energy equals total energy. And we'll assume that this is not time varying, all right? So that the wave function is what's called a stationary state wave function. It's not evolving with time, okay? Now, for those of you who have or are in the process of taking a course by the name of linear algebra, you may recognize this as an eigenvalue problem, such that the function that satisfies this is an eigenfunction. That is to say, psi would be an eigenfunction in this equation, and the e's would be eigenvalues of the equation. So that's one way to think about it. If you're not familiar with that, that's fine, don't worry about it. This is ultimately what we want to try and end up solving in order to figure out what the wave function actually is, and not just come up with these trial things that I'm throwing around up here. Okay. So what we will do next time is look at the simplest possible case of solving something like this. For me, the simplest possible case would be the one in which the potential energy is 0. And I have confined an electron to basically, you can't see my table in front of me here, but imagine I have walls on the ends of the table, and I have a little marble that's rolling back and forth. Its potential energy, we could easily say it's 0, right? It's definitely not changing on a horizontal surface, and it's confined, such that I have an edge of the box or an edge of the table over here and another edge over here, can't get out. So it's got a 0 potential energy inside here, and it's basically got an infinity of potential energy if it were trying to leave, which means it can never leave. So tomorrow we will attack what's known as the particle in a box problem, in which the potential energy is 0, and we are going to then look for the allowed energy states in a box of some width with an electron in it. Okay. So we will pick up with that tomorrow. Looks like we're just about out of time today. So I will bid you fair weather and good tidings. And I think I will be catching up with you tomorrow. Like I said, I will be posting the PLC a little bit later today, such that it will be open and ready to go. And homework's at 8. Like I said, if it's not Thursday, maybe it was Wednesday. I know it's this week, and I'm pretty sure it's not today. So I'll refresh myself on that, and we'll go from there. And in the meantime, I will see you tomorrow.